Great morning, everyone. Welcome back. Today, we are going to add the ratio test to our toolbox of convergence tests for series. It's a little different than the ones we've already learned, since it's only going to determine absolute convergence. That is, the ratio test is not going to be able to detect conditionally convergent series. It's going to be a little too powerful to pick up on those subtle differences. I've written here a couple examples of situations where the ratio test is going to be very helpful. The ratio test is going to be most often useful when the terms of the series have exponentials in them, or factorials in them, or some combination. For example, I've got n over 5 to the n here, that's an exponential. 1 over n factorial here, that's a factorial. We're going to see when we take ratios of these things, they're going to cancel out nicely. Which ratio are we going to take? Right here at the bottom of the screen, this is how we're going to perform the ratio test. We must first evaluate this special limit, the ratio of absolute terms. What's happening here is I'm taking the ratio of an plus 1 over an. So I'm really asking, as n goes to infinity, how much bigger is the n plus first term than the nth term? If the n plus first term is bigger than the nth term, so the terms are getting bigger and bigger and bigger, then this limit is going to be large because the numerator will be larger than the denominator. If the terms are getting smaller and smaller and smaller, this ratio will be fractional because the numerator will be smaller. So we evaluate this limit, the ratio of absolute terms, and we use that limit, if it exists, to perform the ratio test. When you evaluate this limit, again, if it exists, it doesn't have to, it could be infinite, you're going to fall into one of three cases. The first case is, as I said, you get a fractional limit. The limit of the ratios is less than 1, meaning the numerator is smaller, meaning as time goes on to infinity, the terms are going to be getting smaller and smaller and smaller. The ratio is fractional. And if that's the case, the series converges absolutely. Notice this isn't convergent, and notice that the limit of absolute ratios, again, this isn't going to be able to pick up conditionally convergent series. Now, if the terms are getting bigger as time goes on, meaning one of two things, either the ratio is bigger than 1, meaning maybe the numerator is 5 times bigger than the denominator, or if the limit of the ratios is infinite, meaning the terms are just getting bigger and bigger and bigger like crazy. They're not even a multiple of the previous one. They're just going crazy. They're reaching infinity. The ratio is infinite. Then you have a divergent series. Seems pretty simple. You take a ratio of consecutive terms in absolute value, an plus 1 over an. If it's a fraction, less than 1, you have an absolutely convergent series. If it's a number bigger than 1, you have a divergent series. If it's infinite, you have a divergent series. There is one number missing from these two scenarios, so there is a third case. What if the limit is exactly 1? What if the series that you're evaluating, the terms, as time goes on, get closer and closer to each other, so they basically become the same? The fraction is 1. Eventually, the terms are all the same. Well, then you got to use a different test. The ratio test is inconclusive if the limit of the absolute ratios is 1. So keep that in mind. We're going to do a couple examples. But keep in mind that if you take the limit of the ratios in absolute value and you get 1, you have to use another test. For our first example, let's look at the series negative 2 to the n over n squared. Again, when I see an exponential in a series, my mind automatically thinks, let's try the ratio test. So let us try the ratio test. Let's take the limit of absolute value, or absolute ratios. So an plus 1 over an. Look at this limit and see what happens. So this is the limit. So n goes to infinity. So the n plus first term, negative 2 to the n plus 1, over n plus 1 squared, all over the nth term, negative 2 to the n over n squared. And this looks like it could become a messy limit to evaluate. But we're going to see that exponentials, and then we'll see factorials, are going to be prime candidates for simplifications in these types of fractions. Because I'm going to rewrite this fraction. Instead of dividing by a fraction, I'm going to multiply by its reciprocal. So negative 2 to the n plus 1 over n plus 1 squared times n squared over negative 2 to the n. I'm going to do this from now on without mentioning that that's how I'm dividing fractions. And you see this negative 2 to the n up here cancels with the negative 2 to the n on the bottom. And I'm left with just one negative 2 on the top. And over here I have n squared over n plus 1 squared. And I think you see what's going to happen here. I'm going to expand this and evaluate this limit. The absolute value of negative 2 is 2, and the limit of n squared over n squared plus 2n plus 1 as n goes to infinity is 1 over 1, because the leading coefficient of n squared is 1. The leading coefficient of n squared plus 2n plus 1 is also 1. So this limit is 2, which is bigger than 1. That means that eventually every term is double the previous one. So by the ratio test, this series diverges. That's all there is to it. Take the limit of absolute ratios, and if that limit is bigger than 1, the series is divergent. Our next example is going to involve factorials and exponentials. So we're going to mix them up a little bit. Again, I see factorials and exponentials. I think in my head, use the ratio test. So I take the limit of absolute ratios. And because this is a fraction, I'm going to write the first term, or the n plus first term. Be very careful that the plus 1 is inside of the factorial and not outside of the factorial. And that the n plus 1 is the exponent. It's not added to 100 to the power of n. And divide that by the nth term, which is the same as multiplying by its reciprocal. And we get this. We know how to simplify the exponentials. This 100 to the n cancels with that 100 to the n. And we get 1 over 100 left over. Let's now simplify the factorial function. Now we know n plus 1 factorial is just start at n plus 1 and multiply by every integer below it. So n plus 1 times n factorial. You just peel the n plus first term off, and then the n factorial is left behind. And you can see now this is going to simplify quite nicely. N plus 1 over 100. And the limit of this is infinity. So the limit of absolute ratios is infinity. It has no bound. So by the ratio test, the series diverges. Our next example is going to be another combination of exponential, -3 to the n, and factorial, 2n plus 1 factorial. Do note that the 2n plus 1 is what's being factorial, so we have to be careful with parentheses when we're evaluating these. Because it has exponentials and factorials, I know that I'm probably going to want to use the ratio test and evaluate the limit of absolute ratios. So let's do that now. The n plus first term, -3 to the n plus 1, over 2 times n plus 1 plus 1 factorial. Again, be careful of the parentheses. I'm replacing the n with the n plus 1. So it all has to go in there as a unit. Divided by an, so I'll multiply by the reciprocal, 2n plus 1 factorial over -3 to the n. Now I'm going to simplify this a little bit by first canceling the -3 to the n, which leaves me with just a -3. And over here I'm left with a 2n plus 1 factorial divided by, that's 2n plus 3 factorial. I'm going to expand 2n plus 3 factorial a little bit so that I can cancel some things out and get an expression that I can evaluate the limit of. On top, I'll have 2n plus 1 factorial. And on the bottom, I'll have 2n plus 3, that's the first term. And then I go down to the next integer, 2n plus 2. I go down to the next integer, 2n plus 1 factorial. So I'm not going to peel the first one off like I did last time. I'm actually peeling the first two terms off and leaving the rest. Then that's going to cancel. This is why factorials and exponentials work so nicely with the ratio test. This is the way that they are defined. It makes them very suitable for cancellation. Excellent. So the limit of absolute ratios is the limit of -3 over 2n plus 3 times 2n plus 2. Sorry, that should be a 2. And I'll take the absolute value. So this is the limit as n goes to infinity of 3 over 2n plus 3 times 2n plus 2. Constant over quadratic, that's 0. 0 is less than 1. So by the ratio test, the series converges. Absolutely. Therefore converges. Let us now finish up this lecture by answering, why is the ratio test inconclusive when the limit of absolute ratios is equal to 1? We know it's absolutely convergent when the limit of ratios is less than 1. We know it's divergent when the limit of ratios is greater than 1. But why inconclusive when it's equal to 1? And I'm going to answer that question by considering two series, one divergent, one convergent. But they're both going to have limits of absolute ratios that are equal to 1. Our first example, the series 1 over n minus 1. Now, this is a divergent series. You can check that by doing a comparison test by comparing this to the harmonic series. But if I take the limit of absolute ratios, which is the limit as n goes to infinity, the n plus first term is 1 over n plus 1 minus 1 times, well, divided by 1 over n minus 1, so times n minus 1 over 1, which is the limit as n goes to infinity of 1 over n times n minus 1, which is equal to the limit as n goes to infinity of n minus 1 over n, which is 1 over 1, because the top has degree 1, leading coefficient is 1. Bottom has degree 1, and its leading coefficient is 1. They're the same, so it's just the quotient of the leading coefficients equals 1. So it's a divergent series whose limit of absolute ratios is equal to 1. Let's look at a convergent series. 1 over n squared plus 1. This is a convergent series. Again, you can do a direct comparison test with the two series, 1 over n squared, if you'd like to prove that this is convergent. But I just want to look at its limit of absolute ratios. The limit as n goes to infinity of 1 over n plus 1 squared plus 1 divided by 1 over n squared plus 1, so multiplied by n squared plus 1 over 1, which is the limit as n goes to infinity of n squared plus 1 over, I'm going to write this as n squared plus 2n plus 2. And because that's a quadratic divided by a quadratic, the limit of this is going to be the limit, it's going to be the quotient of leading coefficients, which is 1, because the coefficient on n squared is 1n squared, and 1n squared on the bottom. And there you have it. Two series that both have the limit of absolute ratios equal to 1, but one converges and one diverges. So it's not enough information to know that the limit of absolute ratios is equal to 1. It's not enough information to determine the convergence or divergence of a series.